Welcome back. We are at lecture 56 today. The goal today is to finish up trigonometric integrals, just a couple of secant tangent integrals that we'll work with. There's a lot of interrelationships between secant and tangent. Even without calculus, there's still some interrelationships with the Pythagorean identity, which I didn't write that down yesterday. We need to write those down as well, because those might come in handy. This is actually being taped on a Friday. The Saturday that follows this day is State versus Carolina. So I wanted to leave no doubt today where my allegiance lies. So, no, I don't have any Carolina blue on. I can guarantee you that. The only thing Carolina blue I have in my house is my wife. She went to Carolina. So, but she's been converted. There are a couple of rules. You never cheer against your free tickets. If somebody gives you free tickets, you cheer for whoever that person would have cheered for that gave you the free tickets. I got free tickets to the Carolina game. Okay, well there's an exception to that because you go to State and your sister goes to Carolina, and I mean, you've got a little diversity going on in your family with State, Carolina, and App. So, but normally if somebody gives you tickets, you never cheer against your free tickets, and you never cheer against where the paycheck comes that actually feeds and clothes your family and buys your home and puts your son and daughter in college. So you never cheer against that either. So my wife conveniently agrees with that. We did a problem yesterday, or started a problem. So let's pick up on that today. Finish the secant tangent integrands. If you'd see her, you met my wife, you'd say, man, she's so pretty. What is she doing with him? You know, and I think the same thing every day. I mean, it's like, I checked the mirror this morning and I say, what is she doing with me?
You're saying this to her on purpose, aren't you?
No, she knows it.
She's going to watch it.
No, she knows it. I mean, I've made that very clear. It's like, what's wrong with your vision, you know? You guys, some of you are laughing too hard. That's not nice at all. All right, derivative of tangent is secant squared. That might come in handy. Derivative of secant is secant tangent. May or may not come in handy depending on how we approach this problem. A couple of other things. There is a Pythagorean identity. I mean, everybody remembers the good old sine squared plus cosine squared is 1. That's an easy one to remember. There's one that has the secant and tangent in it. How can we start with this one and come up with the one? I don't know, maybe you remember it. Do you remember the secant squared, tangent squared Pythagorean identity? Secant squared equals tangent squared plus 1. Secant squared equals tangent squared plus 1. Now, is that Catherine speaking or
it's my notebook.
the chart in the back?
I have it in a very place right
now.
So
now that's convenient, but on a test, that little reference page is not at your disposal. So how can we start with this one that everybody knows, right? Sine squared plus cosine squared is 1, and we want to come up with the secant squared, tangent squared version.
Divide by sine squared.
Divide by
sine squared.
Sine squared?
Cosine squared.
Cosine squared. One of the two.
Right.
Okay. There are 3 Pythagorean identities. This is one of them. The other 2 you get by dividing this one by sine squared. That's one of them. And the other one you get by dividing by cosine squared. We want cosine squared because sine squared over cosine squared is tangent squared. And that's the one we want. So sine squared over cosine squared. Cosine squared over itself.
1.
And 1 over cosine squared is
secant
squared. So if that kind of is not right at the tip of your tongue and you forget that and you need it, you can take the one that you do know, divide everything by cosine squared, and you're at the one you want. And you feel reasonably confident that that's the right one. All right, so that is secant squared in terms of tangent squared. What if we want to solve for tangent squared?
Secant squared minus 1.
Secant squared of x minus 1. So those 4 things may or may not come in handy on a specific problem, but it's nice to kind of at least refresh ourselves with those interrelationships of secant and tangent. Now, this particular problem, which let me write this on the other page now. What can you observe from this list of 4 things that we wrote down end of class yesterday and beginning of class today? What could come in handy on this problem?
The derivative of tangent.
Derivative of tangent is secant squared, and we've got one of those, right? So that might be the first attempt. At least it has some merit that it might work. So if all that squiggly underlined stuff is going to be du, then we're kind of thinking back to the u being tangent. And has a chance of working. It's not guaranteed that it's going to work. If we try to rewrite the original problem in terms of these things, what is the original problem?
U cubed du.
Okay, so it worked, right? U cubed du, that's a whole lot easier looking. So that's u to the 4th over 4 plus c. And we're going to review a lot of this earlier antiderivative, indefinite integral, definite integral stuff today. I'm hoping that as we go back to those topics that you'll say to yourself, I know all those. I've been doing those for weeks now. Now, a few things we can spend some time on, the sigma notation that we haven't touched for a while. But most of it is, this has been cumulative in this unit of material. So u to the 4th is tangent to the 4th over 4 plus c. Would this squared tangent cubed? Let's try something else and then see if we can decide that that would also work or it would in fact not work. Same problem. Sometimes there's just a way to do a problem, and sometimes there are multiple ways. Let's say we wanted, because there's a secant and a tangent here, right? So let's say that we want to send those out to the right somewhere. So we'll take one of these secants aside and one of these tangents, and then we'll write secant of x, tangent of x, dx. Is that equivalent to the original integrand? So the purpose is there a chance that this stuff, secant tangent dx, could that be du? And if that's du, what is secant of x, tangent of x, dx? What is that the derivative of?
Secant.
So could we kind of reconfigure this problem to be a function of u, and then all this stuff out here that follows would be du? Well, that's already secant. So the real issue is, could we convert that into a secant?
Yeah.
And the answer is yes. What is tangent squared equal to?
Secant squared x minus 1.
Secant squared minus 1?
Mm-hmm.
So let's try that, see if we can solve the same problem a different way. And then you realize that sometimes you can make a different choice and you can still get to a similar solution, an equivalent solution, without having just one way to do the problem. So this secant of x at the top, we're going to leave alone. This tangent squared is going to be, what did we say that was?
Secant squared minus 1.
And then we've still got this secant of x, tangent of x, dx out here to the right. All right, so let's put these together. That'd be secant cubed minus secant. So we wanted all that to be a function of secant, which it now is. And in terms of our choice for u and du, what is this integrand now?
U cubed minus u times du.
Du. So there's u cubed minus u, and all of this stuff is du. A little different looking integrand, but it was a different choice that we made for u. And the integral of u cubed is u to the 4th. Integral of u is
U squared.
u squared over 2. And we'll put a plus c, and then we'll replace u with what u represented temporarily. Secant of x to the 4th over 4. Secant of x squared over 2 plus c. Are those answers the same? Here's the other answer.
Yeah, if you combine. No, I don't know.
The other answer was tangent to the 4th over 4 plus c. Don't look the same. How could you go about justifying that there are two possibly very different looking answers that are in fact equivalent?
Because a tangent is like the derivative, and then you take the two secants.
Okay, we have interrelationships, right, between secant and tangent. So we could, for tangent, we could actually call this tangent squared squared. And for tangent squared, we could put in what? Secant squared minus 1. And if you'll check that, I bet you'll get this. And if you don't get it exactly, what's the most they could be different?
C.
By a constant. Okay? If, in fact, they are different, when I put in for tangent squared of x, if I put in secant squared minus 1, and if I squared that out, in fact, let's do that. It's not that tricky. That'd be what? Secant to the 4th of x. The middle term is twice their product. And the last term is the second term squared. And everything gets divided by 4. Same answer? This is the same. That was the same as our other answer. That became what? 1 over 2? Became secant squared of x over 2? Now we've got a 1/4, which is, I guess, absorbed in the constant. If they differ, they have to differ by a constant because this is an indefinite integral. So here there's a 1/4 plus c, and the other problem there's just a plus c. So they appear to be different by a constant. So two methods, different looking answers, but they are equivalent answers. So sometimes you have more than one choice. Actually, to tell you the truth, I'm not sure what's going to happen on this problem if we're going to have two choices, but I know we're going to have one. So let's do one more. Tangent cubed. I think we just have one option here. So we could kind of send out to the right a secant squared and then write everything else in terms of tangent. That's not going to work. We can't send out a secant squared because we don't have a secant squared. So scrap that one. We could send out to the right a secant tangent. That's going to be possible. Same integrand, right? I took one of the tangents out of here and left a tangent squared. This is the only secant, so I sent it out there to the right. So if that's the goal, is to make that du, then what is the u choice? If du is secant tangent, then u is secant. Now, it seems a little backward to do it that way, but you've really got kind of two possible things you can send out there as du. A lot of times that'll determine it. Now, you can make your choice for u. Think ahead, what do I need to have out there if I choose that for u? I need to have a secant and a tangent out there.
Change the tangent to
right.
secant.
But if we're going to change this problem to u's and du's, we've got the du's taken care of. Looks like we need to do a little adjustment there. For tangent squared, we need to replace that with
Secant squared.
So now our integrand looks like that. Distinctly different looking, but equivalent to what we started with. So in terms of u and du, what do we have?
U squared minus 4 du.
And all of that stuff is du. Everybody feel confident from that point? You can do this problem? u cubed over 3 minus u plus c. Every time you see a u, replace it with secant of x. So that's the only way, unfortunately, to do this problem. The other way will not work because we don't have a secant squared. Questions about that? So there is more to the problem, but confident you can take it from there. All right, let's talk about our test, which is next class for us, Monday. It does cover 4.9. And I think we did not skip any sections. Let me make sure this is the case. Up to and including 5.7. We just basically did our last subtopic in 5.7. We're not testing over all of 5.7, so we're not responsible. You're not responsible for trig substitution at this point. Again, that clarification is for this group of students in the classroom today, not necessarily for subsequent semesters that are watching this on DVD. So just check your pacing guide to see where your test starts and stops. Probably close to this, but maybe not the same. Okay, so let's go back section by section. Maybe hit some things that we haven't touched on kind of on a daily basis since we covered them. So that was our first introduction to antiderivatives. So you were all giving me that glazed look like, what are these things? But you now feel pretty confident with them. So we basically, all the derivative rules, we throw them in reverse. So if you know the derivative of natural log is 1 over x, then you know the antiderivative of 1 over x is natural log. And there are a few subtle changes like absolute natural log of the absolute value of x, just to ensure that we can actually take the natural log of that quantity, since we're kind of manufacturing that solution on our own. But if you look back to this section, which you should, look back at your notes, look back at web assigned problems that were surrounding this, I'm hoping that seems pretty easy. Chapter 5. I guess the emphasis here is on areas, because we know that's one of the applications of a definite integral, is it does give us the area under a curve. Now this was approximation. So we're taking skinny little rectangles and adding them all together, and we're approximating the area under a curve. You're not going to have a test question that will ask you to find the area of the skinny little rectangles and add them all together to approximate the area under the curve. Okay? We now have better ways to do that. And if you want to do a numerical approach to integration, that is yet to come in this chapter. That is probably the first thing you'll do in 241, where they talk about numerical integration. Sometimes it's necessary because you don't have a function. You just have data points. Well, right now we're in that part of the course where we have functions, so I'm not going to ask you to use the left endpoint, use the right endpoint, use the midpoint of each subinterval, and approximate the area under the curve. Not a test question, unless you would choose, and I'll have an addendum on your test in particular. Now, this was included in this section because the authors were addressing a velocity curve, and they were adding up the areas of the skinny little rectangles under the velocity curve. So this was some time in seconds, whatever the units are, and this axis was the velocity axis. So you had this curve, and from time 1 to time 2, they kind of validated that the area under a velocity curve was in fact a distance. What are the heights the heights of these skinny little rectangles are velocities, so they are, I don't know, something, I'll just put a unit to it, feet per second. What are the widths? Well, the widths are in seconds, and what do you get when you take feet per second, which is height, times width, which is seconds? What happens to the seconds? They cancel out, numerator and denominator, and you're left with feet. So when you take feet per second times seconds, you're left with feet, and the authors address this. What is the answer then? What's the area under a velocity curve? It's a distance. So that did fit in with that topic, but I'm not going to ask you to approximate areas under curves. And we've done more of this since then. We've taken a velocity curve, found the area under it, distance, an acceleration curve, found the area under acceleration, and that was what? That was a velocity. All right, somewhere in this area, and I'm not exactly sure at this moment where it exactly fits in, but when we're trying to go from approximations to bridge that gap to how do we find exact areas under curves, we went to the appendix. In the back of the book, we went to Appendix F, and that was sigma notation. And I know you're wanting me to say that sigma notation will not be included on the test, but that's not going to happen. Okay? Sigma notation will be a test question. So basically, this is the way we get from approximations to exact area. So we'll start with summation. So we're going to add a bunch of things together. They happen to be skinny little rectangles, but we're not going to do that numerically. We're going to start with the first one, I equals 1. We could also start at I equals 0 and adjust the functions to handle this, but this works, so let's just kind of keep it simple. Inside of the sigma notation, the argument of the sigma notation, we want to have the height of each rectangle. There's the height of each rectangle, and it describes it in a scrolling way. So we start at A. So our first height that we want we have slid over from our starting value, we have slid over 1 delta x. So that's going to generate the height of the first rectangle. To generate the height of the second rectangle, we go over another delta x. So there's our scrolling variable. So we keep moving over 1 delta x, then 2 delta x, then 3 delta x. That keeps generating the different heights that we want. The width of each rectangle is just delta x. And I don't want an infinity there. I'm sorry. Eventually I do. I want an n there. So we're going to go from I equals 1 to n. N could be 5 or 15 or 30 or 600,000. But now we want n to approach infinity. So that becomes exact area. And in fact, we have another way. This is kind of like the definition of derivative, and then we had shortcuts for derivative. This is the definition, kind of long way, of finding the area under curve. And we also have another way of finding area under a curve, and that is to integrate what amounts to the top boundary of the function for the duration integrated with respect to x. So am I going to ask a kind of a simpler problem that has you doing this? Yes, one of these. Do we need to do one?
Yeah.
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 Let's do it.
Okay, we can set it up. And then would you tell me when you're confident with it and you feel like you could take it from there? The memorization of those formulas, write it on here. I don't think I'll write that one down for you. I think that's kind of insulting that for me to give you that when you're, 18, 19, 20 years old and you know some math and you ask yourself the question, what is 1 added to itself n times? That would be n, right?
Yeah.
1 added to itself n times. I'm not going to dignify that response that Kent gave. But 1 added to itself n times is n. So you need to know that. The others I will actually write down on the test. But you do need to know how to use them, how they fit into that problem. The sum of consecutive integers, I don't know, maybe you remember. Who remembers what that is? You don't have to. I'll provide this for you.
N plus 1 divided by 2.
Divided by 2. So the last number, if you're stopping at 7, it'd be 7 times 8 divided by 2. So that's 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7, right? 7 times 1 more than 7 divided by 2. And this is the only other one then that you would need to use. There is another one, but I'll make sure the problem doesn't use that one. I just want to see if you can do this process without getting too complicated. How's that go?
N plus 1 squared.
2n plus 1 divided by 6.
All over 6. So at least you know kind of what they should look like, but I will provide this for you on the test, and I'll provide that for you on the test. And you'll need those, right, to sub in because you're going to have this possibly in your problem, and if you can't make that substitution, you're not going to be able to get a numerical answer. And you're going to have this potentially in your problem. You're going to have to be able to sub this thing in, or you won't be able to get a numerical answer. So a problem like that, look at that, I almost wrote on that again. Let's say that's our function, and we want the area this long way, this sigma notation way, area under this. From x equals 1 to x equals 4. So what are some things that we might want to do ahead of time before we start subbing into this formula right here?
Go ahead and separate them and change them to the other form.
Okay? There's a delta x in there, right? Let's go ahead and off to the side, let's evaluate what delta x is for this problem.
Great.
What's delta x all the time in any problem?
A minus b divided by
B minus a, so ending value minus beginning value, so the total width of that subinterval divided by how many rectangles you want, and we want n rectangles. So delta x for us in this problem is 4 minus 1, which is 3, over n. So I'll write the generic version one more time, and then we'll just sub into that. So that's going to give us exact area. So if you don't have that committed to memory, I would urge you to do that. That starting sigma notation statement. So the f, well, we're going to use this function, but not yet. What is a? 1. So that's where our x value, so where these skinny little rectangles start is at x equals 1. plus I times delta x. Well, delta x is 3 over n, so I times 3 over n is 3i over n. So we want to do that. And then after we throw that thing into the function and see what it's equal to, then we're going to multiply everything by delta x, which is 3 over n. Keep going, or is that enough?
Keep
Keep going?
Yeah.
So we take that value and we plug it into the position of x in our original function. So we have 1 plus 3i over n squared plus x, which is 1 plus 3i over n plus 1. And then everything in there gets multiplied by 3 over n. So if we square that, 1 plus 3i over n, what's the first term? 1. What's the middle term? 6i over n, so twice their product. Third term of the trinomial when we square it? 9i squared over n squared. Okay, and then we just kind of write the rest of the stuff. So before we distribute the 3 over n, can we group some things together?
Yeah.
Okay, 1 plus 1 plus 1 is 3. And then we're going to take that times 3 over n, right? So that's going to be what? 9 over n. So we've taken care of that, that, and that. Okay, we've got 6i over n and 3 more I over n. 9i over n times 3 over n, which is
27i
n squared, right? Because we've got an n and we're in the denominator and we're multiplying by another n in the denominator. So we took care of that one and that one. And then we've got 9i squared over n squared times 3 over n. So that is what?
27i squared over n cubed.
Keep going? You just want to finish the problem?
Yeah.
Okay.
Take the limit now, just say
Yeah.
all the n's are going to be go to infinity.
Okay. Well, let's leave the stuff that scrolls, and then we'll move the stuff that's not scrolling out front. So everything comes out of the first one, right? 9 and n, and then it leaves 1. And the second one, we can pull out a 27 over n squared. And that leaves I. And the third one, we can pull out a 27 over n cubed. And that leaves I squared. So now let's make our substitutions. And we can go ahead and incorporate the limit now that n, well, let's not do that yet because we can't do that all the way through. What is 1 added to itself n times? That's n. What can we replace the sum of I from I equals 1 to n? Okay, and this will be given to you. Don't have to have this memorized. But you do need to know what to do with it, where it kind of fits into the problem. Sum of I squared, or the sum of consecutive integers squared from I equals 1 to n. 2n plus 1 all over 6. So this one's easy. Doesn't matter what n is, if n is going to infinity or not. I over n times n is just 9. So we've got 27 over 2. So I'll put the numerical stuff together and then the n stuff together. 27 over 6. Now, what happens as n approaches infinity? What happens to this?
Goes to infinity.
That approaches 1, right? Why does that approach 1? Because we have an n squared over an n squared, right? So 1n squared over 1n squared as n approaches infinity. So this thing approaches 1. And what happens to this circled quantity as n approaches infinity? That approaches 2, because what's the first term here? 2n cubed, and then everything else is of lesser degree, right? 2n cubed plus some other stuff over n cubed as n approaches infinity.
2.
That approaches 2. So I think we're done, right? We're done with the n's and the i's, and we should have all numbers left. So 9 plus 27 halves plus 27 over 6 times 2, which would be either 54 over 6 or 27 over 3. And then the rest is combining those numbers. Any question about that? Now, you can we consolidated some. You can potentially do more than we did right here. All right, what else? After Appendix F, then we went to shortcuts for evaluating the definite integral. So in 5.2, finding exact area under the curve without that longer sigma notation, I and n, kind of long method. And really it's kind of hard to separate these. And then a variety of evaluating definite integrals. And we did examples galore in class, and we had questions from WebAssign that gave us different types of situations to look at. So I think we've done at least one of every kind of circumstance we can possibly come up with at this point in time in the course for integrating and then evaluating. So I know you don't need this, but we find the antiderivative, and to evaluate it from A to B, we take the antiderivative at B. So that ought to be something that is old hat, and you've been doing that for weeks. So that sounds pretty important. Fundamental theorem of life. I think I would want to know what that is. So this is calculus. This is the fundamental theorem of calculus. So this kind of formally and officially interrelates the derivative and the integral for us. It says if you have the integral of something, some function of t, and you're integrating it with respect to t, and you're evaluating it from a number, I don't care what the number is, as long as it works in the function, to x. So we're going to integrate it, then evaluate it from a to x, and then we're going to turn right around and take the derivative of that with respect to x because our answer is in terms of x. We evaluated it from a to x. So we have to derive with respect to x. So if we start with f and we integrate it and then differentiate it, where should we be? Back to f. Okay? F is what we started with. We integrated, then differentiated. So we're back to f, but we have f of x. Right? So that is pretty much how the derivative and integral are interrelated. They are inverse operations of each other. If you start with something and integrate first and then differentiate, you're back to that same function. Now, why x? How did we switch horses from t's to x's? Because we evaluated this function of t. Once we integrated it, we evaluated it from x to a number. What happens to the numbers? Well, we differentiate those, and those are gone, right? But we've got this new function of x, and we differentiate it, and we're back to the same description, f, but now it's a function of x. Now, how does this play out in a problem that would be probably the worst case? And that would be, suppose that h of x, I think this is the way it was given to you in the book and in WebAssign, h of x is the integral of, I don't know, let me think of some hideous function here, 1 plus t to the fifth dt, the square root of that. We can't integrate that, nor can we integrate it then evaluate it, so we're kind of stuck. Let's say we're going to go from 3 to x squared. So when that's not just x up in this position, then we've got another issue, the chain rule, to contend with. So if that's h of x, and it's our task to find h prime. So we want the derivative of this integral. So if we are calling h the integral and then we're differentiating x, we ought to be back to the same function, but there's a little subtle twist to it because it's not just x, we're evaluating at x squared. So tell me what to write down for the answer.
1 plus x.
Instead of 1 plus x to the fifth, it's 1 plus x squared to the fifth. And instead of dx, which kind of works here, this takes a chain rule to get us to that point. So don't we also have an additional 2x, right, from the chain rule? Look back at your notes on that day whenever we covered fundamental theorem of calculus. And without going all the way back into the chain rule, if it's not just x, you have to include its derivative here because of the chain rule. So 2x times the square root of 1 plus x to the 10th. Same format as the original function. The new variable is not t anymore. In fact, it's not x, it's x squared. But we've also got that little chain rule baggage that comes along with it. All right, that's 5.4. Real briefly, because this is the most recent stuff. Probably it won't require a lot of your time to go back and review integration using substitution. Let u equal such and such du. If the integrand doesn't have some pieces of du, when is it that we can correct for what's lacking? If it's a number, okay? We need a 5 there. There's not a 5 there. Multiply by 5 as long as we do what else? Divide by 5 or multiply by 1/5. But you cannot do that with letters. In fact, if we could do that with letters, couldn't we just take this x squared and slide it out front?
Yeah.
For that matter, let's just take the whole thing and slide it out front. You can't manipulate letters that are in the integrand and move them at all. But numbers, you really, when you multiply by 5 and multiply by 1/5, that's legal, and it certainly is legal to take one of those that we don't want in the integrand and just move it aside. set it out in front. We don't want it there. We had to have it there to make the substitution work, but it doesn't need to be in the integrand. So you slide numbers out, but you can't slide letters out in front of the integrand. Real quickly, 5.6, integration by parts. I'm not going to give you anything there. And there is a chance that I'm not going to tell you to integrate by parts. So you're going to have to figure that out. Substitution, you might try something in your head. It's not going to work. Okay, I might tell you to integrate by parts, but don't necessarily count on that. So we would be wanting to put the integrand in what kind of a form in order for us to use this? U dv
Times v
minus v du. So we're hoping that when we look at this new integrand that it is workable, or at least more easily workable than what we started with. So you've got to account for the entire integrand, though. Everything has got to be either u or dv. You've got to accommodate all of it in this format. So the parts that we did cover in 5.7, decomposing an ugly rational function integrand into partial fractions. There are really, I guess, technically 4 rules here. If you have a linear factor, so a factor like x plus 1 or x minus 7, what kind of numerator does that get?
constant.
It gets a constant. So as we decompose this, any linear factor gets a constant, so A or B or C or D, whatever. We'll do as many as we need. And if it's a linear factor to higher powers, how do we accommodate that?
Everyone.
Every one of them gets a separate entry, right? A over x minus 1, B over x minus 1 squared, C over x minus 1, the quantity cubed, till we've got it to its highest degree. But that doesn't counteract that. They still get constant numerators. So an irreducible quadratic factor in the denominator, what kind of numerators do they get? They get linear. And by linear, give me an example of a linear numerator that we don't know what they are. AX plus B, CX plus D, EX plus F. And in like fashion, if we have an irreducible quadratic factor to higher powers, we continue to use that as a factor until we've exhausted it to its highest degree. So you could have a AX plus B over the irreducible quadratic, CX plus D over that quadratic squared, EX plus F over that quadratic cubed. If it gets that bad, you're not going to have to finish the problem. But I may have you set one up and just stop at the setup just to see if you knew what to do. And the other part of 5.7 that you are responsible for this test are the trig integrals, sines and cosines, odd powers of sines and cosines, even powers of sines and cosines. The worst case scenario there is where you're stuck with an even power and we make a substitution. Let's get those written down and then we'll stop today. What can we substitute for sine squared of x?
1/2. 1 minus the cosine.
They're the same, right, to that point? Now, how are they different?
Plus and minus.
Plus.
This is plus?
Yes.
No.
Nose minus.
Cosine's plus.
Minus? This is plus? Now, if you need a backup on that, you can do the cosine of 2x is cosine squared minus sine squared, and then take a minute, probably take you a minute, to solve this statement for sine squared of x, or take a minute to solve this. If you solve for one, you have the other, right? The other one is the opposite sign. So this could serve as a backup if you need that to get you these formulas. But that's the worst case in that problem. And I told you we'd be done then, so if we did that, we're done. Test on Monday. See you then.
Do you know where like 5 towns? Is it? That's in like Long Island, right?